Okay, welcome everyone to this week's CDAC webinar. Today it's my pleasure to introduce Samad Hajinazar from the Department of Chemistry at SUNY Buffalo. Samad is a computational condensed matter physicist. He's an expert in materials modeling and predictions using DFT, and in particular has developed machine learning tools for computational materials and analysis of large data sets. He's also contributed to methods and open source code development for crystal structure prediction, superconductivity methods, and molecular dynamics, to name a few. Samad received his PhD in condensed matter physics in 2019 from SUNY Binghamton and was a postdoc there until 2022. He then joined a group of Eva Zurich, one of our CDAC partners, in 2023. And we're looking forward to your talk. Thank you very much for agreeing to give it.
Thank you, Ross, for managing for the event and for the introduction. Hello again, everyone. I'm Samad Hajinazar, working currently in Eva Zurich's group at Chemistry Department in SUNY Buffalo. So in today's talk, I will discuss the various ways in which the challenging task of finding novel materials can be sped up by essentially learning from natural processes. However, before going over the actual slides, I would like to start by describing the specific problem that I will try to discuss today. That's basically why materials prediction is a challenging task and how the presented materials, the following materials will relate to the issue. Essentially, technological needs drive an intense effort to find new materials every day. We are constantly seeking materials that are better at conducting electricity and heat or not doing so at all, materials which are softer or harder and so on. But finding new materials actually is basically harder than finding a needle in a haystack. An immediate challenge which exists is basically the scale of the problem. Different estimations exist for the dimensionality or vastness of the chemical space. I have seen ranging from 10 to the power of 60, or even recently I saw in an article 10 to the power of 100 possible substances or chemical compounds. Just to compare with what we already have, I would like to note that the CAS registry, which is one of the largest ones, I believe includes some less than 300 million chemical substances. Or, for example, ICSD database hosts less than 300,000 inorganic chemical compounds. So basically, what we know simply is just a fraction of what remains undiscovered currently. Traditional experimental exploration of novel materials is bound with several limitations, as we all know. For example, it's prohibitively expensive, it's time-consuming, it's limited by safety and regulation constraints, and further, it is hard, as we know, to reproduce extreme conditions of pressure and temperature in the lab and set up the experiment or synthesize a new material. So basically relying on theoretical knowledge and insight, along with its manifestation in computational methods, seems to be a promising way moving forward. That can help us by either discovery of new materials or by narrowing down the chemical space, the search space, by hinting on possibilities or guiding the experimental synthesis also. Fortunately, and mostly due to the abundance of computational resources, one's impossible tasks, especially the high throughput materials modeling and prediction, seem to be increasingly in reach of the materials community now. Perhaps one of the most important things to mention here is the application of first principles calculations, which practically are the gold standard for the computational materials modeling and prediction. Still, the point is that nothing can prevent us from seeking more innovative ways of reducing the cost of this kind of research. It turns out that looking at the trends and processes of nature is a rich source of inspiration for finding shortcuts to the procedure of finding new materials. This is, in fact, the focus of my talk today. I will attempt to illustrate a few cases where bio-inspired tools and tricks can help us explore the chemical space more efficiently, and will try to show how utilizing these approaches can help us tackle problems of high interest. Now, with this sort of introduction, when we're talking about the theoretical or non-experimental prediction of materials, perhaps the first thing that comes to mind is thousands of lines of computer codes or sophisticated supercomputers and machines. But in fact, one of the very first, and some might argue one of the very important systematic materials predictions predates any of these stuff. And sort of funnily, that was made possible actually by observing the trends in the nature. So somehow related to what I'm discussing today. And that prediction is basically the periodic table itself. We know that by following the trends in atomic weights of the known elements at the time, Mendeleev made some 16 predictions, if I'm not mistaken, which 8 of them within a span of 7 years were discovered, and they were very close to what he had predicted. But this is not, of course, what we want to do. While we know less than enough to solve our problem, we know more than just the basic trends in the elements to merely follow the suit. The state of the art of our knowledge about how the machinery of nature works is the quantum mechanics in the atomic scale, especially. Within the Born-Oppenheimer approximation, various ionic arrangements of atoms basically correspond to points on a high dimensional surface, which is commonly referred to as potential energy surface or energy landscape. And exploring this potential energy surface basically can result in finding various minima, global minimum or local minima of the surface, which are corresponding to the stable and metastable phases of the chemical compound that we are interested in. So essentially the problem for us would be to finding a proper mapping of the Born-Oppenheimer potential energy surface, and then apply some search algorithm, proper search algorithm to navigate the surface and find the stable and metastable phases of the material. So quantum mechanics is the best that we can do right now, but its equations, as we know, cannot be solved analytically for practically any realistic problem. Then, as a result, an array of numerical approaches are developed to solve this problem numerically. Among them, density functional theory, although it's not as accurate as quantum chemistry methods, and it has its own known limitations, but it's practically it's the tool for the large scale materials modeling and prediction right now. While there is a lot that we can learn from quantum mechanics. In particular, we are interested in total energy because that's corresponding to mapping the potential energy surface, and then we can attempt in finding new phases of material that we are interested in. So DFT, although practically the common tool that we are using right now, has its own computational costs. These are just some numbers to give you an idea of what a typical DFT calculation will cost in terms of CPU hours. Most importantly, and relevant to what I'm discussing today, is the computational cost for predicting ground state, to finding ground state through some search algorithm, some efficient search algorithm actually. If this was to be done on a single core computer, this is corresponding to 50 years of calculations. Of course, we are not doing them on single core computers, but this is just to give you an idea of how expensive still is DFT for high throughput materials modeling and prediction. So basically, we need to find ways to reduce this cost and speed up the whole process of finding new materials. And that's where the idea of bio-inspired algorithms come into the play. One of the most important, maybe, and definitely promising candidates to do so are machine learning interactive potentials. But before basically discussing them, just to illustrate a picture of what we're dealing with, it's a long time that we are familiar with classical potentials. They are essentially very efficient uh, tests, or have shown that they are to almost 6 orders of magnitude faster than DFT calculation. They are easy to fit, mostly fitted using the experimental data. But unfortunately, as it is shown in the literature repeatedly, they suffer from the transferability issue, especially when it comes to the ground state search problem. So in this picture, and given the fairly poor accuracy of these models, although they are very efficient, ideally we would like to have something which is reasonably efficient and accurate at the same time. And that's where the machine learning potentials show up. So machine learning platforms in general are increasingly popular tools with a wide range of applications in pattern recognition, in, in fitting and creating predictive models. And they are making their way to pretty much every aspect of our daily life. But in this particular context that we are interested in, machine learning potentials in the literature over the past almost 15 years have been introduced, developed, and applied in various platforms, including neural networks, which are basic form of machine learnings, or the traditional forms, moment tensor potential, Gaussian approximations, and so on. The point with machine learning potential is that unlike classical potentials, they don't have physics. They're black boxes. I just need to mention here that this is mostly regarding the early forms or primitive forms, that they have appeared some forms of machine learning, physics-informed machine learning, and those sort of platforms which are taking advantage of extra information like charge density and things like that. But in any case, they mostly have the huge number of adjustable parameters, again, unlike the classical potentials. So more data is needed to fit them, and usually these data are provided by first principles and in particular DFT calculations. Benchmarking tests have shown that machine learning potentials are some 3 orders of magnitude faster than DFT in calculating energy, forces, and generally derivatives of energy, which is a tremendous speed up basically. And then the hope is that if they can provide good accuracy, they will be a good candidate to be used in large scale materials simulation. In very basic form, this is just showing an architecture of a neural network. So it's comprised of few mathematical units referred to as neurons, which are connected to each other through some adjustable parameters. And the way this is being used here is that we provide a large database of materials, which means having a huge set of structures with their corresponding energies, atomic forces, and so on. Then we try by first converting the structural information into proper input for machine learning platform, which is a fixed length numerical vector, and then try to adjust these adjustable parameters during the training process such that we will get the best compromise and the least error in reproducing the target values, which are energies and forces and sometimes the stress components. The good thing about machine learning platforms is that they mostly they can be represented by algebraic expressions, the output value as a function of input. So we can take analytical derivatives, and that can help a lot in training these models and finding the set of suitable adjustable parameters. A typical workflow starts by preparing a database, then that database needs to be transformed into proper input for machine learning. And then once we have the machine learning input, we start the training process or optimizing the adjustable parameters or weights of the machine learning platform, in this case, neural network, and then we obtain the model. More recently, there has been some interest in making this a sort of closed loop by monitoring the progress in improvement, essentially, in the quality of the model training, and then use the model to upgrade the data and improve the quality of the model which is obtained, which are usually referred to as on-the-fly database generation schemes, which they come in various basically implementations. Now, this is essentially an increasingly popular topic, as we all know, with many developments in various aspects. Here, I will not get into much details about the platform, but I would like to mention just a few practical aspects in construction of machine learning interactive potentials. So one problem, for example, that we might face is when we accumulate the data for various chemical systems and construct machine learning potentials. In this case, tests like the one that you are seeing here have shown that because of the different nature of bondings in different systems, as we mix these stuff, we might get different descriptions for a certain element coming from different models. This is somehow an issue because ideally we want to always reuse the data and avoid regenerating all these databases. And the point is that the error, the scale of the error that we are seeing typically is of the order of the machine learning error itself. So in particular, in the application to materials prediction, which is very sensitive to these errors, this is not really something good. So for example, in this case, it can be shown that with a stratified scheme for construction of model, this challenge can be overcome. So we can reuse the data, and the way it works is that at each stage we just feed corresponding parameters and keep them fixed, and then move on to the next step. So starting from elemental systems, then binary systems, and so on. In this way, elemental subsystems are always described consistently, and binary systems the same, and so on. Then as a result, we will be able to reuse the data while we are creating a large, consistent library of interactive potentials which are applicable to various chemical compounds. Or another very important part is that the generating of the training data set for machine learnings. Machine learnings are extremely sensitive to input data. Essentially, they learn from the data, and they're expected to reproduce or predict samples which are similar to data that they have already seen. They are not extrapolators. They are just interpolating the data. So it is very important to know what we are doing with the arrangement of the initial database. Typically, if you look at the literature, molecular dynamic, ab initio molecular dynamic runs are the way to go for generating machine learning databases for machine learning interactive potentials. It's just you're running various MD simulations at different temperatures, then start sampling them. In fact, you can do that in a smart way, as it is shown a long time ago in the literature, and then collect them and train a machine learning model. However, if you look more closely to the data, you will see that not a surprise that there is a strong correlation between the bond length in the database that you have created. And this is not a surprise because of the nature of the underlying data, which is generated from molecular dynamic, which is within harmonic approximation. But this is not desired for material for ground state search, because it's just an indication of potentially limited scope of the data from which machine learning has learned. So it potentially will have trouble in reproducing structures which are essentially way different than this, including those which are in higher regions of energy landscape. Alternatively, this one can be addressed by just using evolutionary sampling or a scheme like that to essentially generate the data. And as you can see here, the radial distribution function is pretty much smoothed out, especially compared to what we get from MD simulations. In fact, this can be automated as it is done here. For example, in this case, we developed this package, MazeNet, which is a fully automated on-the-fly evolutionary database generation for machine learning application. And all it does is just repeating cycles of evolutionary searches, curing the data, taking care of faulty runs and so on, and finally yields a database of machine learning potential, which is created using the evolutionary sampling, which in few applications we saw, as I will mention later on, how it can perform desirably and reasonably well in predicting new materials. So this is about how we possibly can create potentials, machine learning potentials, and how we can create underlying databases, but are they really working? Now, we can start with some basic tests. These are showing equation of state for some transition metals. And as we can see, the high symmetry structures are reproduced quite well once we compare the performance of the machine learning models with the DFT, which is the reference method by which the data is generated. Also, here is a glimpse into phonemes. The accuracy is satisfactory. That also applies to the formation energy of binaries, and many tests for substitutions and basically setups like that have shown that the produced models can perform well in capturing the underlying DFT potential energy surface. So ultimately, the implementation of these methodologies have been used in many different tests, and they are present in the literature in numerous studies, including those which are dedicated to finding new materials or modeling materials in large scale. Here are just a few examples that I choose here because I was involved in, but as I mentioned, there is a lot more in the literature done in this respect. For example, here, it was an interesting work in collaboration with Romero groups in West Virginia, which using machine learning potentials, we found potentially synthesizable new phases of magnesium, calcium, and tests at higher temperatures. And tests show that not only the energetics were at 0 Kelvin, I would say, which is the setup for DFT, actually, not only the energetics were reproduced very well, but also machine learning potential was, in fact, very good at reproducing thermal corrections. So the discrepancy between machine learning predictions and DFT, whenever it was tested, it was really satisfactory. And also other examples which include predicting nanoparticles of copper, palladium, silver system, and gold nanoparticles, which application of methodologies that I just mentioned resulted in finding unpreviously reported essentially nanoparticles in these systems. So one aspect that I haven't mentioned yet is the search itself. As I said, we have Born Oppenheimer potential energy surface, and in order to find new materials, we need to explore it to find minima. But how do we do this? Let's say that now we have DFT or machine learning potentials which are efficient and accurate enough, but to map the potential energy surface, but we need to explore it and find what we are actually looking for. There is a variety of global optimization problems, algorithms, which are developed and applied to this problem. In particular, there is one which is explicitly a bio-inspired algorithm, and I would like to discuss that in a little bit more detail. That's the that's the evolutionary search algorithm. So briefly, just to show the workflow, we start, let's say schematically, this is the potential energy surface that we are interested in finding the global and local minima of. Typically, a typical workflow in the evolutionary algorithm starts by initializing a population of structures which are randomly generated, only constrained by some chemical reasonable intuitions or basically ideas like bond length or angles of the unit cell. Then we just locally optimize the structures that we have generated. And once we do this, we find the fitness. In this context, fitness means how structures are good, essentially, for our purpose, which explicitly is how low their energy is. So the lower the energy, the structure is fittest. It's better. It's closer to what presumably would be a minimum on this potential energy surface. After assigning fitness and considering the fitness measure for different structures, we select a subset of them as parent structures and then apply the evolutionary operations. Generally speaking, evolutionary operations include mutations, and crossover mutation is just random distortions of a single structure, but crossover includes operations which mix two structures and simulates breeding in the nature and creates an offspring out of those two parent structures. Once we did this, for example, just to show you an example of these tasks, how they are done, they might be better illustrated in the context of clusters. For example, this is an example of a mutation applied to a small cluster. We just take a part of that and rotate it and create a new one, which is different than the previous one by a random distortion. Or in this case, we can mix two clusters by swapping core and shell and create a new one, or cut them in half, or take a portion of each and create a new structure as offspring of these parents. In any case, once we came up with the new population as a result of applying these evolutionary operations, all it's left is just to redo this cycle. I mean, we start by locally optimizing these structures and then evaluating fitness and so on until a certain number of iterations are exhausted or a desired measure in terms of convergence of fitness has been achieved typically. Now, this is, as it has been shown in the previous studies conducted by many groups, this is a really efficient algorithm for global optimization of chemical compounds, including those examples which I showed you. At least two of them were basically done using the evolutionary search algorithm. But we can still, in fact, utilize what we learn from the nature to make this process work even more efficiently in different applications. And next, I will show you just an example of basically a trick which can be used to make the evolutionary search algorithm performing better in the context of here nanoparticles. So let's start by this tiny, simple example. This is just 55 atom cluster for, let's say, a transition metal. It has a very high symmetric shape, and pretty much any search algorithm converges to this structure quite quickly. based on what we know, essentially, we expect that if we set to search for a 54 atom cluster, one less atom than this one, we would expect the lowest energy structure to be something like this, which in fact is at least in some of these simple transition methods that I just mentioned. But in reality, especially if the search scope is limited, this structure is very hard to find. So you will probably see all sort of bizarre uh, uh, combination of atomic configurations, but not this nice high symmetry structure, which is just missing one particular atom. This is shown here just as an example of this issue, which I mentioned here. We compared the performance of the machine learning in combination with evolutionary research in a systematic search for nanoparticles over this range for copper and silver and palladium. And we sort of intentionally kept the search duration short because ultimately all we do is just to gain more efficiency. That's the whole purpose of all these efforts. Now, as you can see, there were many of these ground states which were missed during this search, and just we couldn't find them. Now, as an example of a trick which I just mentioned, which we can learn from nature, we came up with this idea that different populations in the evolutionary research can essentially co-evolve. In this multi-tribe scheme, instead of running independent searches, we just initiate a batch of searches which are similar in size or close in size. And then once in a while, we exchange the seed, meaning we just take the best structure from the nearby tribe or population and merge it into the current population, and then continue. So in this way, after a while, which, for example, this population has converged to the proper ground state, when we take the best structure from 55 atom tribe and merge it into the neighboring 54 atom tribe, it immediately captures the best structure, and that tremendously speeds up the whole search process. Just to show you the outcome, once we did this with everything being the same, we just missed a handful of structures in the same systematic search over the range of sizes for these elements. And further, we just compared the performance of this co-evolutionary scheme with machine learning potential and compared that with a fairly popular classical potential, in this case, Gupta potential, for which a systematic study was existing for this particular system. And as you can see here, there were so many improvements in terms of the configurations which are lower in energy, more stable compared to what was reported in the literature. And these were just found using the co-evolutionary research based on machine learning interatomic potential. Now, one particular problem which is very interesting is in application of these approaches and these tool sets is not only finding the ground state, which is the center of all I have discussed so far, but also find materials which are not only stable, but also have a specific character, like, for example, some given hardness value, or they are superconducting, or, for example, they have a certain class of symmetry or geometrical aspect. This is an elevated problem, very challenging one, still a challenging one, and usually it's referred to as inverse design problem in the literature. Now, next, I will discuss that how we can adopt this whole formalism, in this case, the search algorithm, and basically take a slightly different route, a variation of the search algorithm, which I discussed to address this problem. Let's get back to the basics of the evolutionary research. As I mentioned, a crucial step in the evolutionary research is finding the fitness of candidate structures. As I mentioned, that's a measure of how low their energy is. Typically, this can be translated in this simple mathematical expression. So we obtain a number between 0 and 1 for every structure, 1 being the fittest one, 0 is just the one which has the highest energy. And then this can be used to basically as a basis for selecting patterns for the future generations in the evolution research. Also, we can just schematically demonstrate that with something like this plot, which the fitness value, the normalized fitness value, is illustrated as a function of geometrical coordinates. This workflow is implemented in Xtolop code, which currently I'm working on in Zurich's group at SUNY Buffalo. And the whole workflow, just to give you an idea, is essentially similar to what I explained. The Xtolop code has this capability to be interfaced to various total energy calculation approaches, including classical potentials, first principles calculations, or through scripting to machine learning potentials, as we have done some tests on them. And we used to find ground state for the desired chemical compound. In many applications, the efficiency and performance of this algorithm and this implementation has been demonstrated. But in this particular case, what we are interested is just extending the scope of the problem and find materials which are not only stable, but have some particular interesting property. This is, first of all, I need to note that this is a problem which has been essentially attempted in the literature in previous years. In this context, what we tried and did in Xtolop was to generalize that and make it as a general user-friendly and basically easy to use tool set to find materials of some desired property. The way that this can be essentially done is by generalizing the fitness function. In this case, the fitness essentially, or traditionally, the fitness is determined based on energy. Alternatively, this can be extended so we can have a multi-objective fitness function, and this multi-objective fitness function includes not only energy, but any desired property that we have included, only subject to the constraint that the overall weights are normalized and add up to 1. This will be corresponding to a change in the geometry of the fitness with respect to the geometrical coordinates. For example, as just schematically shown here, we have some points on the some structures which with some given fitness, I would say traditional or regular fitness, which might be better off in the new with the new generalized fitness, or they might be less fit. In general, the traditional fitness gives priority to the structures which are having lower energies. But since we are mixing that with other properties, and other properties are not necessarily consistent with the energy in terms of where their minima is located, then we are having a trade-off between the suitability in terms of energy and in terms of other properties. In some way, this multi-objective optimization scheme works like the Robin Hood of the energy landscape. So while there were some which were fortunate and eligible to be parents of next generation, it just takes some less fortunate ones and elevates them and gives them a chance to be parents to the next generation structures. As a result, what we will have is just some potentially metastable phases, those which were not lowest energy, lower energy structures traditionally, but they have higher energy, so they're metastable. But on the other hand, they have a they are more likely to possess the particular character that we are interested in. So this multi-objective evolutionary scheme is implemented in the Xtlopt code. We have modified the workflow slightly and added a step. We made Xtlopt able to be interfaced to virtually any external code which calculates any desired property as long as it can be represented by a single number, like the case of energy. So as long as you can use anything which can calculate any property as a number, this can be used with Xtlopt. Various examples include, I mean, the possibilities are essentially limitless. It can be, for example, a coordination number, symmetry, it can be uh, electrolyte property, or it can be synthesizability. And these are examples which I will quickly mention. So, but the bottom line is that right now, Xtlopt is able to work with any external code to basically read in the properties which are calculated by them and merge them in the evolutionary search in order to find functional materials. Before just briefly mentioning the examples that I just said, let me just say a few words about the Xtlopt and the recent development. The multi-objective search functionality is available in both command line and graphical user interface of Xtlopt. It can be easily invoked, and it includes various optimization schemes. It can minimize a property, it can maximize it, or even it can be used for constraint search. That's just to filter the pool of the structures that are being created based on some given property. And also, it can provide you a live and illustrative status of the run at each stage, both in the command line and text environment, and also in the graphical user interface. Now, next, I will tell you very quickly about two examples of this multi-objective search scheme. These are developing works. They are not published yet. We're just working on them, but I will include them just to show you how this scheme can work and help in more efficiently, hopefully, find materials that we are interested in because of some properties that they might have. So let's start by molybdenum disulfide example. We know that there are some synthesized phases for this material, for this compound. Here are some just shown as an example, which are relevant to the next picture that I will show. Now, in this context, there is a machine learning model which can predict the synthesizability of a chemical compound. It's developed in Kat Khodai group in Chicago and called XIESPP. So for this test run, we interfaced Xtlopt with this external machine learning platform. And at each stage, we use the synthesizability likelihood of the candidate structure using this machine learning model and use that as input for the generalized fitness in the multi-objective search process. Overall, here is just an overview of the search which was conducted. And as you can see, this evolutionary search not only found these experimentally reported phases, but interestingly, we were able to find a new phase that is not reported in ICSD or other materials databases. And this particular phase has, according to the machine learning model, has a fairly high synthesizability likelihood, and it's only 3 MeV per atom above the ground state, according to, with the DFT setup that we used for all these evaluations and simulations. Or another example of multi-objective search includes electrolytes. For LACL compound, we know that it's a compound that potentially can form electrolytes, and that can be manifested in some free charges which are not localized on ionic positions in the crystal structure. And topologically, it can be checked by looking at the electron localization function to identify whether there are some free charges in the region of interest or not. There is already one metastable phase of this material, which is synthesized and it is known. Here you see the electron localization function value as these points in the structure. Now we use the code critic2 and interface that to Xtlope in multi-objective search. After running first principles calculation at each step for each candidate materials, we just transferred the structure to this external code, and it evaluated the electron localization function for that candidate materials. And then we got the information, Xtlope got the information and assessed the fitness of that structure. In this search, basically, again, we were able to find another candidate phase, which is not reported in the literature. And moreover, it was not found in the traditional evolutionary research. Not using the extra objective or extra property in this case. And it's just lower in energy compared to this synthesized phase, perhaps, but the synthesis route and condition will be different. And the point with this scheme that is basically tested by one of our group members is Stefano, that it's parameter free, unlike some previous examples in the literature. It doesn't require extra layer of analysis of the information regarding electron localization functions. So as a result, it can be freely used at different pressure values, which is an interesting possibility in searching for electrolytes. So these were just very quickly some examples, very recent and developing examples of the methodology which is implemented. And that was just to show how this multi-objective search can help us finding materials of interesting properties. And overall, I hope I was able to just give a picture of how these nature and bio-inspired approaches and tricks.
Samad, your mic cut out.
Samad, can you hear us? Samad, we can't hear you on this end. Can others hear him?
No.
Hello, can you hear me?
Yes, now we can hear you. We couldn't hear you for the last 3 to 4 minutes.
Hello, can you hear me right now?
Yes, we
Right
can.
now, yes.
Mhm.
Okay, sorry about that. I don't know what happened. So what I was trying to say was that these were just developing a new examples of the methodology that I described, and I hope this was I was able with these slides to give a picture of how bio-inspired and nature-inspired approaches and tricks can help us in speeding up the materials prediction. And finally, I would like to note that what I described, especially in the context of machine learning potentials, was not meant to be a comprehensive overview of the field, because there are lots of new developments like universal potentials and materials informatics, which were not included here. And at the end, I would like to acknowledge my colleagues, those in Zurich group, which I'm working with right now. And these last two examples included work conducted with these fellow group members, and also former colleagues, which some other examples and applications that I showed were done in collaboration with them. So that would be all. Thank you, and I will be happy to answer any question if there is any.
Thank you very much, Samad. Very interesting work and some very
Thank you.
examples. Yeah. So questions, comments? Just unmute yourself, raise your hand, put a comment or question in the chat. Maybe I'll start with that very last example, which was very interesting. So you have a new phase that you predict. And now, what are the PT stability limits of that phase? So where would one look in PT space to make that material, make that phase?
Yeah, I mean, Stefano did these test searches, and I mean, I talked to him. He hadn't yet done the phonon calculation, so at this point we don't have that information yet. That's something to further investigate, of course.
Mm-hmm. But how about just the pressure volume equation of state?
I don't think it is done, but Stefano, if you are, I don't know if he is here. Yeah, I don't think, no, it is not done yet.
Okay, well, we should follow up. Sasha, go ahead.
Question about high pressure calculations. So convergence to the target pressure going like stepwise. There's several different pressures. Do you generate your machine learning potentials at each pressure?
That's an interesting point, because you know, yeah, as we know, they are highly dependent on the nature of database. The workflow that I described here, which is an automated basically package to generate the model, includes elevated pressures. So you set up desired range of pressures and generate the data at each pressure. And in most cases that I mean, examples that I showed, the machine learning models which were used included higher pressure data as well on top of the zero GPA data. Yes.
So you're generating this potential on fly. Suppose you have BFGS process, right? In the several steps, several pressures. How does it work practically?
Well, the overall workflow works like starting from conducting I would say preliminary search using just the underlying first principles. In this case, we use VASP, mostly DFT with VASP. So once you do this search, which is conducted at different pressures, like I believe by default 0, 10, 30, and 50, up to 50 GPA. Once you were done with this search, these data are being collected and used to fit a machine learning model. And then next, and in the all subsequent cycles, what you do is just to do the same search, but instead of DFT, using the machine learning model, which is produced in the previous cycle. Then once you do the search again at a range of pressures from 0 up to 50. I mean, of course, you can change it. These are just default values, which we found suitable for the applications that we were interested in. So you do the search again, and at each stage, the code looks through all the structures which are generated, finds the unique ones, and submits them for DFT calculations. And based on the discrepancy of the DFT energy and the energy which is calculated by the machine learning, it just estimates how bad the machine learning model is or how good it is on the other hand. Then if the structure is not reproduced well with the machine learning, means that it is not well represented in the database at this point. So it samples those structures along with some samples from their optimization trajectory, calculates them with DFT and adds them to the database, and this whole cycle repeats for as many number of iterations as you set up the whole basically task. At the end, at each stage, you will have few number of structures which are not well represented by machine learning. Then you add them to the database, and in the next cycle, the performance of the model will be better. And ideally and hopefully, at each cycle, the number of structures which are not good in their machine learning description reduces. This is something that we used to do manually, and this package, all it does is just a wrapper to conduct this whole operation and all these tiny tests kind of automatically, and just repeating these cycles.
Thank you. Over.
Sure.
Thank you. More questions? So how far along are you with the multi-objective search package? Is it released? Can others use it in the same way that you're using it now?
Thanks, Ross. Yeah, that was a good point. Maybe I should have commented on that. It is not officially released, but it is actually even publicly available on GitHub. So it can be downloaded, it can be used, and we will be happy actually to provide instructions for anyone which is interested in using that. But in terms of progress, we are in the middle of writing the manuscript for a new release and making the code, merging that with the main basically repository of the code. So the development is finished. We just need to release it sort of officially.
Great. Okay, thanks.
Sure.
All right. Any more questions or comments? If not, thank you very much, Samad, for a very nice talk. Very interesting work.
Thank you, Ross.
Thank you all for joining us, and see you next time.
Thank you.